Integer divisibility, prime and composite numbers. If we take a positive integer larger than 1, so 2, 3, 4, 5, and so on, we can find all of its positive factors by repeated trial division by integers smaller than itself. Now, every integer a has at least 2 factors. 1 divides any integer a because a times 1 is a, and a divides itself because 1 times a is a. And these 2 factors, 1 and a, I shall call the trivial factors of a. Of course, sometimes we can find more than 2 factors for an integer. So 15 is 1 times 15. It's also 3 times 5. So 1, 15, 3, and 5 are all factors of 15. So 15 has 4 factors. Now, if we take an integer a that is larger than 1, and it only has the 2 trivial factors 1 and a, then it's called prime. If we take an integer a that is larger than 1, and it has more than the 2 trivial factors, then we call it composite. In this case, it must have at least 3 factors. Now, since any integer a greater than 1 either has the 2 trivial factors only, or it has more than the 2 trivial factors, then any integer a greater than 1 is either prime or it is composite. The integer 1 is a special case. It is neither prime nor composite. We only use the terms prime and composite for integers that are larger than 1. Now, the only type of number that can be prime is an integer, but in fact, we usually talk about the prime numbers rather than the prime integers. To refer to the set of all prime numbers, we use this P symbol, which is in LaTeX Blackboard bold font. Perhaps surprisingly, there is no standard symbol for the set of composite numbers. If we look at the first few integers larger than 2, we see that 2 is prime, 3 is prime, 4 is composite, 5 is prime, 6 is composite, 7 is prime, 8 is composite, and 9 is composite. And the numbers in the green list are prime because they only have the trivial factors. The numbers in the red list are composite because they have more than the trivial factors. They have at least 3 factors. A prime number is a number that only has factors 1 and itself, so we can find the prime numbers by removing composite numbers from a list of integers. The composite numbers are those numbers with more than 2 factors. So they are the numbers that are in the multiplication table of some other integer. This approach to finding prime numbers is usually called the Sieve of Eratosthenes. Eratosthenes was a Greek mathematician who recorded the method, though he probably didn't invent it. Firstly, we remove all but the first number in the 2 times table. Then we do the same for the 3 times table, and then the same for the 4 times table, and so on. And that procedure removes all of the multiples of 2, 3, 4, 5, and so on. It leaves behind only the prime numbers, i.e. only those numbers which are not composite. So firstly, let's mark 1 as neither prime nor composite, like so. Now, the only factors of 2 are 1 and 2, so it is prime, and we mark it in green. We now remove all of the multiples of 2 by marking them in red. Now, that process did not remove 3, so it must be prime. We mark it in green. And now we remove all multiples of 3 from the list that have not already been removed. The next smallest integer still in the list is 5. It has not been removed, so it must be prime, and we now remove all remaining multiples of 5. And we continue in the same way with the remaining integers in the list. And so, having coloured in our Sieve of Eratosthenes, we can copy the numbers into the set P. From smallest to largest, the primes go 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. The sieve method allows us to find all of the primes in a given list of integers. But of course, we may wish to find out if a specific integer n is prime or not. And one way to do that is to perform trial division with all of the integers between 2 and the square root of n. If n is a very large integer, then you will of course need to write a program on a computer to perform this task. It would take too long by hand. We can now note the following facts. 2 is the only even prime number. And apart from 2, all prime numbers are odd. And why is that? Well, if e is an even integer, then e has the trivial factors 1 and e. But since e is even, 2 divides e. So e has at least 3 factors, and therefore cannot be prime. And finally, although all prime numbers are odd, with the exception of 2, there are of course odd numbers that are not prime. And so we can illustrate the prime and composite number sets on a Venn diagram as shown below. The big rectangle is the set n, the set of natural numbers, i.e. the set containing 1, 2, 3 and so on up to infinity. N can be partitioned into the odd and the even integers. 1 is neither prime nor composite. The set P of primes has one element in the even integers and the rest in the odd integers, whereas the composite numbers divide rather more fairly between the odd and even integers. So we have composite 4, 6, 8, 10 and so on, but also composite 9, 15, 21, 25 and so on.